Oxygen, one of the gases that is found in the atmosphere and the most abundant element, whose structural formula is as given here. This is a double covalent bond composed of two atoms. Therefore, this is a molecule of oxygen. Therefore, oxygen is a diatomic homonuclear double bonded molecular compound. Occupies about 21% of air, and overall, when you compare it to all other elements in terms of abundance, it occupies about 45% of the Earth's crust and atmosphere put together. Laboratory preparation, you can use either potassium chlorate or hydrogen peroxide. Here, these are the conditions. You heat potassium chlorate in the presence of manganese dioxide, you get potassium chloride and oxygen. You heat hydrogen peroxide in the presence of manganese dioxide, you get water and oxygen. There can be other experiments, but these are some of the two. For experiment number one, this is the arrangement here. Your potassium chlorate is heated by using a Bunsen burner there and delivered through upward delivery. You obtain your oxygen, and the product of what remains in this test tube is a salt, potassium chloride. And so you collect your oxygen, and you use it whatever you want to use it for. You can test it and other things. Number two, the equation number two, you have hydrogen peroxide giving you water and oxygen. This is the arrangement here. So you've got this catalyst here, manganese dioxide or manganese 4 oxide, and then you keep on dropping hydrogen peroxide in this round bottomed flask here, and what you obtain is a gas which is going to be oxygen, which will pass through this delivery tube into this beehive shelf, then the gas jar there. So it's also delivered by upward delivery. You cannot deliver it by downward delivery because it's less dense than air. It's less dense than air, so it will not really be collected properly. Down here is a caution. Potassium chlorate may be explosive, so care must be taken when using potassium chlorate. The above reaction or method can be used to prepare oxygen by using potassium permanganate. So it means potassium permanganate can also be used to prepare oxygen, but I think these two can suffice for now. Industrial preparation of oxygen. um, by fractional distillation of liquid air. Therefore, it's prepared by fractional distillation of liquid air. Air is the main source of oxygen. Okay, get air, then you do as I'm about to explain down here. The air is filtered of its solids. Therefore, the first thing is filtration. Solids like dust particles and smoke and all other small things that may be in the air. The second one is the air is cooled to about negative 80 degrees Celsius, at which water and carbon dioxide are removed as solids. Therefore, CO2 and water are usually frozen at this temperature here, then they are removed. Okay, so you remove dust particles by filtration, they remove carbon dioxide and water after cooling or freezing the air, therefore cooling the air to the point of CO2 and water freezing. The remaining is compressed further to allow the remaining is compressed further, then allowed to expand slightly. Compressing air or compressing a gas increases its temperature, and expansion of a gas uh, causes it to be endothermic. It reduces its temperature. Therefore, when it is compressed, it gains temperature. Then when it's allowed to expand, it cools. Okay, it cools, like extremely cools. Okay, it's more like a fire extinguisher. And you puncture a fire extinguisher, which is a gas containing gas like CO2. There's that cooling effect you feel. So compression warms up the air and rapid expansion cools it. So the air here is allowed to expand slightly but rapidly. Okay, the process of compression and rapid expansion is repeated until the temperature goes below negative 200 degrees. Okay, negative 200 degrees. This is the temperature, at this temperature most of the gases liquefy. Okay, the solution of liquid air is passed in a fractionating column, and oxygen is distilled at negative 183 degrees Celsius. Therefore, this is the boiling point of oxygen and stored in tanks or cylinders for use. Physical properties. Oxygen has no smell, slightly soluble in water, less dense than air, neutral to litmus paper. Therefore, it doesn't affect the color of litmus paper. And then it has no color. Some other gases like chlorine, fluorine, they may have colors that we're able to see, but oxygen has no color. Identity test. It relights a glowing splint. Therefore, if you're burning a splint, maybe a matchstick, then you blow off the flame, and what remains is the glow. When you introduce that glow to a jar containing oxygen, it will burst into flame again. So it relights a glowing splint. Physical properties are done, though there can be many more apart from those, including things like boiling point, density, and the like. Chemical properties of O2 or oxygen. I've expressed them in form of equations. So I have water plus oxygen gives you water. Therefore, it reacts with hydrogen. Oh, I meant hydrogen plus oxygen. So hydrogen plus oxygen gives you water. Oxygen reacts with hydrogen to give you water. This reaction is very exothermic, very exothermic. Number two, supports life through respiration. Okay, so I have an equation there for a hexose sugar like glucose reacting with oxygen to give you carbon dioxide and water. There's also energy here because respiration yields energy, and it's the most important aspect of respiration, followed by water. Carbon dioxide is usually excreted out of the system. Number three, supports combustion. Okay, external combustion, reaction of burning of substances in oxygen. Therefore, I have an equation there like methane plus oxygen gives you carbon dioxide, water, and also energy. Okay, that is why combustion or things that can burst or combust in oxygen are mostly used as fuels. So supports burning or combustion. Number four, forms basic oxides with group 1 and 2 metals and even other metals from other groups. It forms oxides whose solubilities may differ. Therefore, oxides of group 1 and 2 are mostly soluble, while oxides of transition metals, for example, are not likely to be soluble, but they are still basic in nature. By soluble, I mean soluble in water. So examples are two equations there where we have calcium reacting to oxygen giving me calcium oxide, then magnesium plus oxygen giving me magnesium oxide. These two are soluble in water. They can dissolve in water to great extents. Number five, forms acidic oxides with non-metals. It forms acidic oxides with non-metals. Examples are carbon plus oxygen gives me carbon dioxide. Carbon dioxide dissolves in water to give you carbonic acid. Here we have sulfur plus oxygen gives you sulfur dioxide. Sulfur dioxide dissolves in water to give you sulfurous acid. Okay, sulfurous acid. These can also, the acids or these gases, when released in the air, especially sulfur dioxide, can actually form weak solutions of sulfurous acid, which can bring about acid rain. Note that phosphorus bursts into flame in oxygen or air without being heated. It is stored under water. So I've written this question because of the equation I'm about to write down here. Where phosphorus, which is also a non-metallic element which reacts with oxygen, it reacts with oxygen to give us phosphorus pentoxide. Phosphorus pentoxide, okay, which is a solid in state. Uses of oxygen, it is used in steel production, therefore, to remove impurities. It is burnt through metal so that other elements like carbon and other impurities can form oxides with the oxygen and then are removed from the steel or from the metal. Number two, in welding, therefore, an example would be the oxyacetylene flame. Acetylene is a gas and oxygen is also a gas. So they burn to simply create this very hot flame that can be used in welding, therefore cutting of metals and welding. In hospitals, respirators or respiratory machines, oxygen is used. To restore life in polluted lakes, okay, therefore you pump in oxygen so that bacteria can respire properly and thrive. In firefighting, the firefighters carry oxygen tanks when they enter those buildings full of smoke and carbon dioxide. They carry oxygen tanks and also part of fuel in space rockets. Part of fuel in space rockets. Even in scuba diving, the uses can go on and on. Pollutants. Some oxides are pollutants. An example is sulfur dioxide, which, if released into the air, can form weak acids. Actually, if released in air, can form weak acids with raindrops to bring about acid rain. Carbon monoxide is a poison to respiration. Nitrogen monoxide can form weak acids with water as well as nitrogen dioxide. Lead oxide is also an oxide which can be a pollutant if allowed to be in the environment, including in water. So these are some of the oxides that are pollutants, which result from oxygen. Oxides that are pollutants. The last part there is ozone. Ozone is also known as trioxygen. Okay, it's a molecule of oxygen which is composed of three atoms. It's also known as aka trioxygen, an important gas that prevents harmful UV radiation from reaching the earth. Therefore, ozone filters UV rays from the sun and other giant stars out there in space, and prevents UV rays from reaching us, ultraviolet radiation from reaching us. Therefore, ultraviolet radiation can cause cancer and other undesirable effects to humans and even other animals and plants out there in the environment. So basically, this is where I end with oxygen. Look out for more other videos on other gases, on non-metals. Remember to subscribe. Bye bye for now.